Hello, today we want to talk about SIL Arithmetic and how to use it to design safe and secure systems. So our motivation is to build system services from components that are less rigorously developed than it would be required by the according domain-specific safety standard. It sounds a bit odd. Why would we actually want to do that? Basic motivation is we want to have a simplification of the development process, because if we have less strict requirements by the safety standard, for example, then also the analysis effort that we have to provide is basically lower, and this could also bring a cost efficiency of the overall system development. But to make this somehow meaningful, we have to explain this further. But before, we want to talk about criticality as such in systems, where we have, for example, in a system multiple services and their criticality is at different levels. The criticality is something that is actually derived from the environment. So to describe somehow how critical this particular service is to achieve the mission of the overall system, and if a service has a certain criticality, then according to the safety standards we use in this particular application domains like ISE 61508 for automation, or DO 178B or C for avionics, or ISO 26262 for automotive domains, then we would also have for a higher level of criticality, we would also have more strict requirements to actually develop this particular service. This means the so-called safety integrity level for this particular service is, for example, higher than the other one. And another specific interpretation of criticality comes from Westall 2007, which has a particular focus on timing assurance, which is basically relevant for real-time scheduling. Interesting is also to discuss our general model here that we consider, because we separate our implementation from the specification. So we have implementation of a service as tasks inside the system, but from the outside, with the environment, we just specify them as services, and these services we have here, for example, 2 SM and SN. They can be then provided by different tasks. We see here, for example, there's also 2 modes, which means the system can switch between 2 scheduling modes, and each mode has, for example, a different set of tasks that implement the particular services. Or for example, in one mode, maybe a service is not even active at all, so there's no task, for example, for a particular service. While in our example here, in both modes, both services provided. But there's one interesting pattern here, is this service SM. This would be provided by different tasks in mode A than in mode B, tau 1 and tau 3, while for the second service, it's always provided in both tasks, in both modes, by 2 tasks, tau 2 and tau 2 prime. And the interesting pattern is here that we have here, to achieve a higher assurance level, we use basically the implementation for this service in redundant form. So task tau 2 prime is a redundant execution of task 2, which means if one of those tasks would fail, then this service would still be provided. And this particular pattern of task redundancy we use here to motivate SIL Arithmetic. So we have our level of criticality that is derived from the environment, or let's say dictated by the environment, and from this particular service, of course, it also propagates internally to the individual tasks. And the idea is here now that depending on this criticality, we would need a certain assurance level for this service, but we actually develop our tasks that implement this service with less strict integrity level, but at the same time use them both tasks to implement this service in redundant execution, and then argue that if this service is basically provided by two tasks in redundant form, that the overall assurance level is of course higher than a single task, because if one of these tasks fails, still the service will be provided. That's the basic idea of SIL Arithmetic. This is also, mentioned in some of these safety standards, that this might be a way to actually develop a system. But of course, in general, one has to do this on a careful level to make this a meaningful pattern. We want to just here provide an example with a UAV, an unmanned aerial vehicle, where we have simplified system consisting of 4 services. Service 1 is the basic flight control. Then we have service 2, some Earth monitoring. Then there is some service 3 is the communication with the station, and service 4 is some particular logging of some task events. And then we see all these services on the right side, they have a different safety integrity level. And in particular, we want to look here in service S3, because here we have a task redundancy between tau 3 and tau 3 prime. And so they both provide this communication service with the station, and together this should be safety integrity level of 2. And if we now assume that we have a fault, for example, and for whatever reason the system cannot execute, for example, both tasks anymore. So, for example, tau 3 might not run. Could be the reason, for example, a mixed criticality scheduler, once it runs low on resources because one computing element has failed, or maybe the execution time is higher than anticipated. So it cannot provide the full execution of all the tasks. And so we have here tau 3 has, for example, failed, and effectively what now is there to provide this service is now only a component that by itself has a safety integrity level of 1 it was developed with. But nevertheless, the criticality of the service, is still the same, because this is dictated by the environment. So we want to provide here in the system a way to basically take care of this particular pattern. And when we, for example, schedule a system, and this would mean that if this assurance level of S3 after the failure of one task is basically reflected only with this lower integrity level that this task was developed with. So we want to have our mixed criticality scheduler built in a way so that it can treat this service S3 based on its original application dependent criticality. And this, in other words, means our scheduler should treat this task tau3 prime with an increased importance to achieve this. What this exactly means is, of course, it depends on the concrete mixed criticality scheduling protocol. There's different variations that can be taken as an input, but it has to be modified to somehow consider this pattern as we described here, so that once, for example, one of these particular redundant tasks has failed, that the other one is now treated with a sufficient importance, so that the overall SIL level, that what the corresponding service actually has, is still somehow reflected in the mixed criticality scheduling protocol. And this has then to be developed for any kind of mixed criticality scheduler that we want to use here. And for us here, it's basically just to motivate that this is some further work we actually want to do. So summarizing from this talk, we actually have shown SIL Arithmetic and also have motivated it. And we have shown that actually this pattern of task redundancy for SIL Arithmetic is something that has to be taken into account by mixed criticality schedulers if we want to use them together with SIL Arithmetics to really provide a sufficient safety integrity level of this particular service in case that, for example, one of the redundant tasks that implement it fails. And our own future work is to propose a modified mixed criticality scheduler, for example, that takes care of this particular pattern. That's it for today. Thank you for your attention.